for Mimic to, I'm sorry, for ClarityNLP to run. And if I hit start ingest, it's going to throw back and say you can't do this. But in fact, there's only actually one, if I'm correct, Trey, one absolute required field, which is report text. This has to have, you have to put something in for report text. All the other fields will give you a warning if you don't put them in, but you can proceed without the other fields. The system will simply automatically generate a date and automatically generate an ID and automatically generate the other elements. But you do need to select text. But in the case of Mimic, I have all the fields I need. I have the patient ID, which is subject. I have the report date, which is the chart date. I have a report ID, which I think is just the row ID in their case. I've got a report type, which is the category. And if I open up Mimic, which I probably, you'll basically see in Mimic, maybe I'll open up with like the text thing so it doesn't blow everything up. What this basically does is I'm just looking. TextEdit usually somehow magically opens huge files relatively quickly. But what we'll do is you can see that these categories are all in there, and then finally I can pick the text. And once these are selected, I can hit start ingest, and it will ingest it into the Clarity Solar instance. I could also say, well, I don't have a category, and so I'm not going to select anything, and I'm gonna let it automatically do, or I'm going to do like. I don't want to use the CSV here, and I want to assign a manual category to all of these documents. Say I had a list of clinical trial reports, and they're of a particular type. Say they're trial follow-up or something like that. I can just assign a report type directly, and I can just say I don't want any of those. And so this basically allows me to put in static or dynamic fields. But something else I can do is I can add a custom field. And I can say I want to have my own field, which we'll call, let's call it, insurance, something like that. And I can give it a name, I guess, like insurance. And this attribute and this thing called adders and adders, it really has to do with the fact that you can mostly leave it. It has to do with Solar if you've got multiple fields in one, if you're doing an array or things like that, it handles it a little differently. But basically, I can say I'd like to make a new field called insurance. I'm going to pull it in from this file, and I'm going to, these just give you some options that you can do, make it required, so you have to field in that type of thing. And then if I put this in, I now have this new field called insurance. And if in my CSV I had an insurance field, I would then simply assign that there. And so what you can see here is that I'm basically able to import both the standard Clarity required fields as well as the any custom fields that you have. These custom fields will now all be available to you when you're running your Clarity analyses and your document selection and all that. So I will pause after talking, I know, a bit briefly about the ingestion UI to ask if there's any questions about it.
Just a question. For example, when you try to find your patient ID in your Excel file, so is that already as you have a row with all subject IDs with all those patient IDs, or is that text and it's just how does it find your patient ID in the text? How does the CSV file look like?
So in this particular CSV file, which I admit is very odd because I opened it in Word, but if I zoom in here, if I zoom in here, what you can see is that in Mimic, I have a row ID, which is 1. I have a subject ID, which is the patient ID. I have some admission ID information. I have a chart date, which is here. I have a chart time, which is blank. I have a store time, which is blank. And then I have a category, which is my document category. I've got a description, which is just the word report and so forth. So in this, and then I've got the text, which is just all of this text.
Okay.
So in this particular CSV, yes, I have that's the type of information that's just going to like a second one. Seems to be, well, here it is. Yeah, so here's just the second one, different patient, etc.
So we could just reformat our data to just have this similar format.
Well, you can assign. You mean if it's not a CSV or
if it's not a CSV, or it is a CSV, but it doesn't have all of this in this kind of line by line type of structure.
So
it has most of this actually, but
if it's not line by line, we could look at it. But you mean so like you've got maybe the file, the information about the patient ID is separate from the text, that type of thing.
So it just requires some preprocessing.
If you want to use the built-in ingester tool, it would require some processing. But if you wanted to, we've also used scripts for ingestion and things like that. But if you wanted to use like this built-in tool here, you would want it. Again, the fields can be anything, but you would want to have it so in your CSV you could access at least the text and the patient ID. I would also make the point that we use the word patient ID, but in fact, for many of our things like a clinical trial, we're actually we ingest on the subject level, and that subject could be a drug, that subject could be a trial, that subject could be whatever level you want to analyze or you would want to consider. So that's why subject is actually typically behind the scenes what's being used as the term. We'll do a future session where we walk through the clinical trials database, the AACT database, and look at how you would ingest data from the AACT and be able to run analyses at like a clinical trial level rather than at a patient level. All right. We covered last week how to run NLPQL. I'm not going to go back in detail because we did that, but I wanted to include it just because for those following along or who later want to run this notebook locally, I wanted to show how that would be done. We most commonly do run our NLPQL, oftentimes from a Postman or any other type of curl, however you might send something to an API, and typically it goes to the 5000/NLPQL target. We do have a UI now that allows you to run. So we have an NLPQL runner, which lets you basically lets you paste in your NLPQL and just run it directly from here. So you don't have to have a Postman going. And we have some examples in there where you can take a look and you can just see some examples as well, and you can load them in and you can just run them as well. So those two methods would probably be the most common if you're just running, not in a demonstration example. But when you are in a demonstration example and you want to work through, in this case, like a notebook, we have a set of kind of notebook helpers. So what I'm doing here is I'm basically just loading in things that let me run Clarity directly in a notebook. And if you wanted to run this locally, there's a URL variable that you would just want to change to be whatever your, if you're running localhost in a Docker instance, you would do that. Otherwise, you could change it to something else. So that basically enables you to run Clarity directly from a notebook as opposed to from the APIs. All right, we're now moving into our topic of the day, which related to just projects and interesting things that have come up. Today we're talking about cancer. We're actually talking about a solid cancer, in this case about prostate cancer. And we want to walk through some examples that highlight some of the functionality that we didn't cover previously, but that we think comes in kind of handy. And then we'll go into some deeper, more sophisticated algorithms and talk about some integration of different pieces. So starting from the very basic use case, where we simply would be looking for a positive assertion of prostate cancer or prostate CA in a record. We talked last week about you can use something called Term Finder to simply find terms, but that the provider assertion function lets you find a non-negated patient as subject non-hypothetical. It sort of automatically puts in all the various features. And so, as we talked about before, all that's really required is a name for what you're searching for, and this Clarity Core library, and then basically you just can set a set of terms, and you say, give me a provider assertion. So this is the most basic, and it's really just kind of saying I want to go out and look for stuff, and I will show this example here, and I'm just running it from the notebook. And basically what I've done is I've just sent this NLPQL to the API, and it's returned back some of these things. In the past, you may recall, we kind of were going to these spots, and we were downloading everything from there, and it's fine, but a little bit of a pain. We now have a Resultsviewer, which makes life much easier. We basically see that the prostate cancer job that I fired off is running. If I click here, I can see the Luigi task visualizer, which shows me what's cooking, what's been running, how many tasks are pending. It's a pretty short little job. That job is now done. And now I have results from prostate cancer. So not any real rocket science here, but it's nice to have just an easy way to review, look through the charts. And what you can do with this viewer is you can actually say, well, let me go in and see the full note here. So if I click on the note, it brings up the full note, and so I can understand the context in which this is shown. If I had a more complicated definition, which we can go over examples later, then I could drill down. But basically what this has done is it's produced a very simple way that you can walk through and you can review, is this accurate? Now, all we were doing, we're looking for things like prostate CA and prostate cancer, but this idea with the check, X, and note is that ultimately that's a way that you could very quickly say, I confirm, or I refute, or I have some comment about what was found here, allowing you to then improve iteratively on the performance of a given algorithm. I would say that we would largely agree, and this is just the notebook view of these results here, and what you can see from the, I see, because they're not intermediate, is that why? That's probably why, because they weren't.
Oh yeah, because they were
like final. They were final results. Okay, sorry. I should never type one little modifier into the NLPQL, but I'll just show basically what you have here in these. Oh, sorry. If I use the app here, just a little bit easier, I'll just show you that I'm looking at my cohort, and what you can see that these were all from the radiology notes, just randomly, because we selected 100 random documents, and basically these all came up as radiology notes. So I wanted to move to what is a very, very commonly used modifier in queries, which is document sets. Searching all documents is done, but certainly not probably the most common use case that you would have. Very often you want to control for the type of document that would be used. So there's 4 key modifiers that you can use in creating what's called a document set in Clarity, and that's report type, report tag, filter query, and query. And so to talk about what these are each in an example, so a report type is what we brought in from our CSV, and it's the raw name of the document. Now, Mimic is a bit pretty in that we have names of documents like radiology and pathology. It's pretty clean, but if you look at real-world documents that are out in the world, there's typically many, many names. Things like, for chest X-rays, you could have CXR PA lat, CXR2 view, AP lat chest, all of these different kind of report types. If, for example, I was looking for a chest X-ray, and so report type is one mechanism. You can specify a set of report types that you want to include, but something that we use in designing more generalizable results or generalizable code that can run across health systems is the idea of a report tag. Now, some of you have been part of the NLP working group where we looked through thousands of report types from multiple institutions and found there was so many different types of names. But luckily, there's some really nice resources, thanks to Loink and Radlex, where they have an ontology for documents as well as an ontology for radiology and other procedures. And Trey here developed a really, really nice mapping tool that allows us to incorporate or group things according to a, let's see here, it's not going in there, but let's see. Got try this one. Okay, so this is basically a map, a list of institutions and different just mapping lists that can be created. Some of these are just sort of tests. But basically, to show you an example, here's a set of report types of all different names, and we can tag them. So you'll see in the example, for example, in Clarity here, is what I wanted to do is I wanted to find just chest x-rays. And so rather than having to know the name of every chest x-ray document, at the time of ingestion, I can essentially assign terms or tags to these report types. And then basically I can assign those tags using this report type mapper tool. And that mapping tool lets me say if I wanted to pick, for example, like a PET scan, a PET scan, then I could basically say, oh, I'm interested in PET scans, and I could assign them all to PET. I might want something like a colonoscopy, in which case I might assign everything to a colonoscopy finding, or I might assign it to gastroenterology. And so I could say, okay, we'd like to take colonoscopies, and we want to say these two guys, we're going to tag them with this colonoscopy term. And that then makes it accessible from there. And mapping and tagging is a broader discussion, and the tools behind it are broader. But just wanted to highlight that one way that you can select documents is by name, but another way is by tags. And that makes for a more generalizable NLPQL that can be reused. The third document set tweak you can do is something called filter query. A filter query basically lets you say, I want to apply some type of modifier to the other rules that I've assigned in my definition for a document set. So I might want to limit my subject, but this would be a place where your insurance would come in. So we don't have a built-in clarity function for insurance, but had we loaded in that insurance field previously, we could have said we want patients who match this and that, but we also want to filter by insurance and then put in the name of the insurance that we were looking for. So filter query is a very powerful way to do a great deal of custom filtering. And then the final version is what would be considered a fully manual query. So you don't want to use Clarity's tools, but you want to use the power of Solr more broadly to be able to look and parse through syntaxes. And Solr has things like wildcard searching, fuzzy searching, proximity searching, searching by alphabetic range, doing all kinds of boosting. There's all kinds of different parsers. It's really an awesome language that can do a lot of different things just in its own right, and is a very effective way if you want to create and craft a really, really custom search. You can do that. And so we have a link to the documentation, but I just have this one example here where I'm just looking for terms that a wildcard, and it has a statin after it, and so I'm able to find things like a statin. But I could have also done things looking for misspellings and fuzzy searches and all kinds of other cool functionality. So I will pause there to ask if there's questions about document sets and the idea behind that. All right. Okay, so conceptually, I think pretty straightforward. So we just have an example here where we basically said we want to do what we did before, which was just look for prostate cancer. But you may recall that before everything was in radiology reports that we happened to pick up. So if I, for example, wanted to say I want to look at discharge summaries, then I would just specify document set discharge summaries. I'd make my report list based on the tag discharge summary, which is from the mapper, and then I can run, and ideally this will go and it will do the same thing that was done before. It's looking for the same set of terms. It's still taking 100 documents, but instead of being totally random, I've constrained it to discharge summary. So I should now be getting, here, instead of getting radiology documents, I'm now getting the discharge summary results. And again, I could also have looked at that through the UI and said, that I want to look at this from here, and I could basically pull those and say, okay, these are all from discharge summaries, and I can confirm and read that. Just as a note from the UI perspective. Yeah, go ahead.
Yeah, this is, sorry if this is something that you showed already, but could you show me where do you define, we're looking for prostate cancer, where do you define the synonym of prostate cancer? Is this looking into any type of ontology, or is it just something that you define manually?
Your timing is great, because we're actually just going to talk about synonyms right in this the very next line is talking about synonyms. We can run through that a little bit, and then hopefully it'll be clear, and then we can answer any questions that aren't after that. Does that sound good?
Okay. Yes.
Yes, your timing was impeccable. I scrolled down 10 pixels, and we've got exactly to your question. So, what we just did was nothing grand, right? Because we just looked for prostate cancer and prostate CA, which I manually just typed in to your exact question, and we looked at it across all documents, and then we constrained it to just look at in-discharge summaries. But building out term sets can be a time-consuming process, and we have some nice built-in features to look at, for example, or to create things like synonyms, plurals, lexical variants, and so forth. And Richard Boyd here has made some really great documentation that actually does walk through the functionality of each one of these, how it works, what gets expanded out, where he goes through and describes that functionality. And I think here in the developer guide is probably in even more detail, where he says what the logic is between all of these different, what is a verb inflection, what is a synonym, etc. And so to briefly touch on them here, I have an example where we're just doing what's called a term set expression using some synonyms. And if you do a call that is clarity.synonyms, it uses WordNet. And I think WordNet is built in from Stacy. Is that where we're? NLPQL. Okay, so it's using WordNet. It's using basically just English synonyms. And so we can get English synonyms, and I could have put in cat or dog. It wouldn't have to obviously be a medical term, and WordNet would expand that out. We can also, for example, pluralize, and so here I'm calling a combination where I'm pluralizing and looking for synonyms, in this case on neoplasm. But we also can use an Odyssey-based vocabulary searcher, which would say, find me synonyms for this term from the Odyssey or OMOP vocabulary set. And I am able to call not just synonyms, but also, I believe, descendants and ancestors as well, so that I could say, here's my concept. I want to call all the descendant concepts as well. And here's an example of where we would run some through, and I'm going to show you how you can kind of run these through in the oops. Okay, a lot going on there. In the application, I can go to the result, the runner, and I can actually just say expand terms. And what this will do is it'll take all the terms that I put in here, and it'll go through, think through, and then it'll expand them out according to what I entered here. And it's a bit hard to read, so I'm going to go back to the notebook where I've got the result. But essentially, what this has done is it's expanded my synonyms. So when I looked for the clarity synonyms for prostate, the WordNet synonyms for prostate, this is what I got. When I did neoplasm, this is what I got. When I applied the plurals, this is what I got here. When I looked at the Odyssey synonyms for neoplasm, it gave me a few different variants, in part because SNOMED has things like morphologic abnormality baked in. When I looked at myocardial infarction, it gave me some different things, MI, heart attack, that were not, that are not present in something like WordNet. Here's the WordNet synonyms for myocardial infarction. Here's the Odyssey synonyms. Go ahead, David.
And John, what about, I don't know if this is also in a category of expansion. Let's say that you want to go one level up. So instead of prostate cancer, you want any type of cancer of the male urinary system, for example. Is that something different from expansion?
No, that should be the same. So let's try it and see what happens. So let's start with we'll do myocardial infarction here. Let me delete some stuff, or maybe I'll just repaste this. And let's do, what would that would be Odyssey Ancestor. Is that correct?
Yeah.
Richard, is it Ancestors? All right, so let's just try this one. I'll delete these other guys up here, and we shall see if that expands. Yeah, okay, so we just did Odyssey Ancestors. Sorry, it's a bit hard to read. Let me blow it up here. So we did Ancestors, and what we got was, for myocardial infarction, all of these going from clinical finding, thank you for not very helpful, to things that are a little bit more specific. We could have also done descendants, in which case we would have, well, I should have copied and pasted a little better for efficiency, like copy there. Okay, so we will do Odyssey descendants, and this should produce the descendant list. And as you can see, myocardial infarction then gives me aneuryseptal infarcts, acute myocardial infarction of interior wall, all the things that basically are the much more specific version. I think, David, you were mentioning a type of cancer like prostate cancer and what might happen if we did a similar thing there.
Actually, it's Sergio speaking, not David.
Oh, I'm sorry. Sergio, I apologize. Was that the question about something like prostate cancer and what we might see with that?
Yeah. That's exactly what I wanted to see. That. But then I think that if you query for the ancestors, there are too many. And probably you are interested only in a few of them or in one particular ancestor.
It's a problem we run into quite a bit, and it's one of the reasons we don't automatically, we provide this function for exploration, and then you can run the NLPQL from here, but we don't automatically run it because it can be pretty crazy. Let's see what happens. Prostate cancer itself, yeah, what looks like is that prostate cancer is probably not the term is probably an Odyssey a SNOMED term that may be something like neoplasm of the prostate or something like that. So in order for Odyssey to work, it does need to be able to find it. So the naming has to be a little bit more precise. So are there any general questions about lexical variants? We talked a bit about synonyms. We didn't mention verb inflections, but here's one example of verb inflections where we are interested in looking at prostate and biopsy, and we don't want to take the time to put biopsy, all the different ways that could be done. So we just used the verb inflection for biopsy. So in this case, we're running it, and what you can see is it took verb inflection biopsy, and it expanded it into biopsy, etc. And then I can, we can run that against the results. So are there any questions about the lexical variant, the concept, or any specifics around lexical variants?
So then, how do you expect? Is this something like that you define with code or on the UI of stuff? If you want to use expansion, semantic expansion,
you can define it in the if you want to use the built-in features like the synonyms and so forth, then you can put it in the code. Right now, we've made it kind of a two-stepper where you can put it in the code and then you expand the code and then you can look at it and then run it. And there's an API that just does the expansion. We may ultimately incorporate it so you can automatically just go from the expansion to submission. But yes, you can use any of these directly into your NLPQL code. So moving through here a little more quickly, we just did this look for prostate and biopsies, and it was a very, again, rudimentary search where we looked for prostate terms and biopsy terms, and we just did a search, and it came back with some documents, and I won't go through all the details, but suffice to say it found documents where we had both those terms present. But one of the things that you often want to do much more commonly than just say, is word A and word B, there, would be something where you're looking for term proximities and you want to be a little bit more rigorous. In fact, you might want to set a definition of something that means, for example, we've done studies where we looked at insomnia, and you want to find all the words for poor and sleep. This is the case where I just replicate what we did before, but we used a different approach in this case, which is something called the term proximity task. And in this case, I can define a set of words, a set of terms, 1 and 2, and I can say a word distance, and I can specify should they be in order or they should be out of order. And what you can see here is that if I run this job, it's going to go and say, okay, I'm going to go and I'm going to parse through all these documents, and I'm going to look for ones that have a match. It's a bit perhaps easier to see the results here, but in short, it's going through and it's saying I'm finding terms that have nearby proximities, and it takes a little bit longer because it's thinking through, but essentially, it finds prostate biopsy, but it also finds things like I think there's a few other examples as it finishes up where it'll pull out things that are more like it's not the terms together, but it might say something prostate cancer, comma biopsy, and this and that. So this is just to make the point that if you want to use the term proximity finder, it can often be a handy way to be able to just assign a feature to a presence of terms, and then you can use those in other queries.
Do you have something like this set up for time, or?
So that's a good question. You mean temporal so looking at temporal proximity.
Transparent date by subject or something like that.
So we have the ability to use a date diff, so that if you say I want to find X, and then it'll find the date, and you want to find Y, and it'll find the date, and you say I only want to find things where X and Y are within a day of each other and all that.
Got
yes,
it.
you can
so
do
you can
that.
combine that in a query.
You can. We could probably stand to do some like convenience functions to make it even easier, but yeah, that's in there, and we'll definitely hit that in a future session as well. The last thing I'm going to say before I turn over to Richard for our cooking special is that last week we presented something called value extraction, which is just a really handy function for pulling out values. We looked at NYHA classes, but you can also look at things like measurements with value extraction. So this is a case where we're going to look at prostate volume, and we want to find prostates, and we want to be able to break down more detail about the volumes that are found in the prostate mention. What you can see here is that what it does is it goes in and it finds the terms that we're interested in, and it finds all the measurements surrounding it, and it actually breaks down those measurements in detail. So, for example, in this case, it finds a term. Here's prostate gland is 4.7 by 4.9 by 3.9 centimeters. We break it down. We actually put it into millimeter dimensions, and we produce the information on that basis. Here's one where it's using x 8.6, x 6.5, x 6.6x, etc., and all the different variants by which a measurement might be recorded related to, and this captures the information, provides the individual sizes as well. So this is actually a really, really valuable tool for looking at the size of a mass on a CT scan or a chest x-ray, etc. And it's a generic tool where you could feed it, instead of prostate, I could have put in something like the liver, I could have put in something related to a mass, and it would have, or multiple terms, and it would have looked for the anatomic and then the measurements associated with it. So it's a very powerful function that can be used. But as part of these explorations, one of the things that you'll see come up, and this is the case in our particular example here, which is this idea of Let's go to one that's got a nice example case here. The Gleason Score. We've been dealing with prostate cancer, and it's hard to deal with prostate cancer without looking at one of its common metrics, which is Gleason Score. We're able to hone down very quickly using document sets for pathology, looking at termset, proximity, a lot of neat things. But getting at a Gleason Score, which is has a little complicated representation, is something that we needed to do, and we need to break out a little bit more custom guns to do this. So I'm going to turn over to Richard to talk about the implementation of a custom query, and again, an example of how you can integrate more complex algorithms into your logic with NLPQL.
Okay. Yeah, the Gleason Score, if you're wondering what that is, it's a way to characterize the prostate gland tissue appearance. The Gleason Score is composed of two components. Each component has a value from 1 to 5. 1 means the tissue is homogeneous, 5 means it's very non-homogeneous. You add the two components together to get an overall score from 2 to 10. And in general, the higher the score, the more aggressive or worse the cancer tends to be, the poorer the prognosis. So this is very important to determine the stage of the cancer and potential treatment. So what I'd like to walk you through here is a custom NLP task that can extract Gleason scores from documents. All right, so to do this, you first need to get an idea of how the Gleason scores are actually reported in the text. If you only look for Gleason score 5, say, or Gleason score and then a number, you're going to miss a lot. So we have about 100 documents with Gleason scores in them, and just gripping through them and looking at the different ways Gleason is mentioned, you'll find a lot of variation. I've got a few of the variants here. So first you see Gleason score 7, and then sometimes they add the individual components to the score. Sometimes they're parenthesized, sometimes not. Sometimes use an equal sign, 7 out of 10. Other times they spell out the actual score in words and not a number, etc. There are lots of different variations. So if you sit here and look at this, you can figure out an overall pattern that you could then build into a regular expression to match these occurrences of Gleason number components in the text. And so by looking at this, a generic pattern is first the mention of Gleason, and then a possible numeric score, and then possibly the components with parentheses. So if you just capture that in a set of regular expressions, that's what's in the next section here. I won't go through all this in detail, but you can do it all in one regex if you're familiar with the concept of regex look ahead and negative look ahead. And basically you look for things, if there's a digit, you take it if it's not followed by a plus sign, or if it is followed by a plus sign, you don't take it if there's another digit following it, that sort of thing. So that's what this regex captures, all right? So now you've got the regex, you can use that to scan each sentence in your document and try to match and find Gleason scores. So that's what goes in the next section. The basic logic for that is take your regex, scan your sentence. If there's a match, pull out any components that match, and then check them for validity. And sometimes we've actually found invalid scores in these documents. Like one of our documents has Gleason score 9 plus 10. And that's not possible. That gives you a score of 19. And the components only go from 1 to 5. And so what I think happened there, whoever typed it in hit the plus key instead of the dash key. All right? The score is 9 to 10 instead of 9 plus 10. Anyway, so we have an implementation of that in this code here, this next code section. We have a simple mapping that translates from text to numbers, and then scrolling down, you look at the logic we use here. So what this does is we have sentences provided in a list of strings, and each string is one sentence. You iterate through the sentences, you then attempt a regex match, and there could be multiple Gleason scores in any sentence, so you need to try to find all of them. Then you attempt to match these various named groups in the regex. Python will throw an exception if you look for a group that's not there, so you have to wrap it in try except block. Basically, if you pull out pieces, then you apply some simple logic to see if these scores are actually in range. And if they are, or if they're easily interpretable, like the 9 plus 10 example, you could convert them to integers and then report them in a list of result tuples. Okay, so that's what this result list is. All right, so if you got that function, you have the regex, you can fold that into a custom task that finds Gleason scores. And if you remember from last time, to do a custom task in ClarityNLP, you need to do a few things. First, you write a Python class that derives from a base class we call base task. And the base task helps link and connect your custom task to all the internal machinery of ClarityNLP. Okay, you need to give the task a name that you can use to refer to it in the NLPQL. So this task name variable here, which I call Gleason Score task. Okay, whatever you assign a task name, that's what you use in the NLPQL. So I'll call this Gleason Score task in the examples we show you. And then you have to actually implement the function that does your custom logic. And you override this function called run custom task. And you're given access to the text of each document, and you can also break the document down into sentences if you want. So I chose to work on a sentence by sentence basis. So we call this function get document sentences, and it will tokenize the document text and give you a list of strings, which are the sentences. Then I hand the sentences off to the function I just showed you called find Gleason Score, and that returns a list of name tuple results. Okay? And then if any sentence has a Gleason Score in it, you can just walk through your result list and build a dictionary, which we call OBS here, just for some generic key value map, and then assign keys and values to it. And these keys that you use are what will appear in your result output, say when you inspect it in Excel or within the Resultsviewer. Okay, so for this task, I want to see the sentence that had the Gleason Score in it, the start and end character offsets for the matching text, the actual score itself, which I assign to the value field, and then if components are present, I call them value first and value second. All right? So I just fill those in and write it out with the right result data. Okay, so that's essentially what it takes to do a custom task. And here in this cell 48, you can see a simple NLPQL file that can call our custom task on a set of documents. So we've chosen to use pathology documents because for our document set, that's where our Gleason scores are contained, but also a Gleason score is a pathology result, so you expect to find them there. Then to actually invoke the task, you see I have clarity.Gleason score task. Okay, that's calling my custom task, giving it the document set of the pathology documents. And if you run this, we can show you example output here down below. John's got it pasted in there, and you can scroll.
I'll show you. Yeah, yours got a prettier display. Yep.
Yeah, down below we've expanded to show the full sentence, and then the value and the individual components. So if it says NaN, that means not a number. That means we didn't find a component or a value. But if you look at all the sentences, you can see it did a pretty reasonable job of finding the score and the individual components. Okay. And then if you have more documents and you find it misses some, you just go back and modify your regex or add additional regexes or whatever you need until you're actually finding most of them in your data set.
Thank you, Richard. And one of the things that you can do actually is you can say I want to just look for patients who have a certain value here, and I'm gonna given the time we'll probably skip our preview for next time, which is how you integrate coded data with Clarity, and we have a demonstration of how you could use the Odyssey toolkit to build cohorts in Odyssey, and then you could connect them. I won't go into the details of that part, but I do want to show you how we can really utilize what Richard's done in a pretty cool way, which is I can say I have a set of, in this case, of patients that I've got from Odyssey. We'll talk about that next time. But what I did was I used Richard's Gleason score task, and I said I want patients where the Gleason value is greater than 5. And I'm able to run that task, and it goes out and it grabs patients who match that set of characteristics, and then my final results from my cohort here, it's probably easier to view it in the application, is basically a group of individuals with, right here, who have the values, who have Gleason scores that are greater than 5. So what you can see here is it just going through all those example patients, and I've got the database, all that. So, we have covered a lot today, and I wanted to note that our sort of cooking specials will kind of go more into sort of algorithmic work. We're going to talk about topic modeling next time. And one of the previews is looking at how you use structured data like Odyssey, and we'll look at the different data sources as well, about how you combine. But we also very much want to get use cases from folks on the call that are relevant to the projects they're working on, and we can build out examples and work through them together. So with our last couple minutes, I just want to see if there's any questions or ideas or suggestions that people would like to see at future sessions. Jeff, is there anything that you guys are interested in particular? And
yeah, I think there are probably specific things. So unfortunately, some of the people that Builtin was able to join, but some of our clinical experts I may need to talk to them about kind of some examples that we may want to try to work through for next time. But I think that'll probably be a work in progress.
So we're going to send out an email, of course, inviting folks to submit and just ideas, even if you're just like, here's what I'm trying to tackle, and we'd love to see them.
You can send them to me. We'll
you can send them on to Charity. She's the organizer for the meeting, and of course leads our overall NLP team as well. Was there anyone who this week tried to set up Clarity and ran into problems, or did anyone have any technical issues that they'd like us to discuss offline? Okay. All right. Well, we appreciate everybody's time. We know that there's a lot of different material, and I think once we've got kind of these basics out of the way about working with documents and terms and other things, we can settle into really tackling specific challenges and problems and orient around clinical questions and use cases that people in the community have. So thank you guys for dialing in. I hope everybody has a great rest of your afternoon. So thanks very much.
Thank you.
Thank you. Good night.
Okay.
So I think thanks. That was great. I know you have to run.
No.